this computer. All right, so I have my little chat bar up here. So if anybody sees a question pop up there, please tell me. If I'm not there, I'm going to go ahead and move this to the bottom. So we should see this online as well as live, the functional groups thing right here. I'm going to move this off to the side so that we can do that. And we are recording. So welcome back to Organic Chemistry, Organic Chemistry 1. Obviously, watch the weather. Tomorrow might not be coming to class, but that doesn't mean we're not going to have our quiz on Monday. Today's quiz has been moved to Monday. It'll cover all up to chapter 2 with the intermolecular forces. IR will be reserved for the following Wednesday, for that Wednesday. So we actually have 2 quizzes next week, chapter 2 up to IR, and then Wednesday is IR, okay? That way, we'll make sure we get all the way through it. You have plenty of time to study, and we'll get back on track. Questions involving that? Okay. If somebody online can hit the something in the chat to prove that I can see you, that would be good. Okay, great. Thank you. All right. So what we're going to do today is we're going to continue on our little journey of organic chemistry, and we started talking about the different polarities we had in our different types of bonds and how that translated to polarity of molecules. Okay, now we're going to start talking about functional groups. These are things that give the molecule functionality. I said carbon-hydrogen bonds are fairly nonpolar. They are nonpolar covalent bonds, and therefore they don't do much. That means anytime we have any other type of bond in a system, your ears should perk up and say, hey, wait a minute, that's a different type of bond. That's probably where the chemistry is going to happen. And we call that the functional group because it's the one that's going to function. So we have those, and usually we see these is that they have different characteristics like an atom other than carbon, or a double-double, or a carbon double bond, or a carbon triple bond. So we're looking for those differences from just a regular old hydrocarbons to give us that functional group. Yes? Huh? Oh, there's a question on the chat. Thank you. So the quiz will cover up to chapter 2. The quiz on Monday will cover up to intramolecular forces and solubility. The quiz on Monday will do that. The quiz on Wednesday will go chapter 2, including IR. Okay? So thank you. All right, so functional group. So look for something other than carbon-hydrogen bonds, and that's probably the functional group. So what we'll see there is we have a lot of different things to do this, but carbon-carbon double bonds and carbon-carbon triple bonds count as functional groups because they have more chemistry than a carbon-carbon single bond. Okay, so that's important. Those are our first functional groups. But then we want to do where we introduce what we call heteroatoms. Hetero meaning different than carbon and hydrogen. So oxygen, nitrogen, phosphorus, those are heteroatoms. When you start seeing a heteroatom in there, that might be a functional group. In fact, each of these functional groups is going to have a different type of reactivity based on what atoms are in that functional group. So we need to, number one, distinguish the difference between our functional groups and figure out what kind of bond it has. Is it a polar bond? Is it a non-polar bond, et cetera? And so when we think about that, when we have something like a bond to something other than carbon, let's do carbon, oxygen, hydrogen here, okay? There's a polar bond between the carbon and the oxygen. But there's also a polar bond between the hydrogen and the oxygen. And so this gives us places to do stuff. That hydrogen can do something because it has a polar bond. That oxygen can do something because it has a polar bond. This carbon-oxygen bond might do something because it has a polar bond. Okay, so look for the polarity in the bond, look for those differences in electronegativity to give us ideas about where to see our functional groups. Okay, so that's one way to look at those, but then we also have to think about pi bonds. Pi bonds are functionality too. So our carbon-carbon double bond and our carbon-carbon triple bond count as function. Even though they're not heteroatoms, they're carbon-carbon. That pi bond gives us functionality. Okay, so that means we need to talk about the different parts of a functional group. Hydrocarbons are boring, but we can represent them with a general term that we call R. R can be any hydrocarbon. It can be alkene, alkane, alkyne, aromatic. It just is something organic. But then we're going to show you the distinction and put the functional group on the R group. So the functional group is the thing that's going to do stuff, okay? So, and what we're showing here is that there's a bond between a carbon on this R group, any alkene, alkane, alkyne, or aromatic compound, between the carbon and the functional group, okay? So our functional groups look a little bit different depending on what we use. So if we have something like this, remember this is our structural drawing, that's only carbons and hydrogen. So we have 1, 2, 3, 4 carbons on this structure. And that means all the other things are hydrogen. Do we have a functional group on this molecule? No, we have non-polar covalent bonds, okay? So we have no polar bonds, only sigma bonds. We only have sigma bonds on here. We have no lone pairs. No lone pairs. Polar bond. It's really hard to write sideways like that. All right. No polar bonds, no lone pairs, no heteroatoms, very unreactive. Okay. But let's change one of these bonds. Let's take away this hydrogen and put a heteroatom in its place. OH. Right here. Okay, so now we have a polar bond, so that's different. We still only have sigma bonds, but look at this. There's lone pairs on this oxygen. We have a polar bond here. We have a polar bond here. We have lone pairs. We have a sigma bond, and we have a possibility for this thing to react with the hydrogen, the oxygen, or even between that carbon and that oxygen. So it's the functional portion of the atom. Okay, questions on that? All right. So what we're going to do is we're going to look at different types of functional groups. But before we do that, I want to introduce the topic of substituents, alkyl substituents. Okay, so alkanes are the things to carbon and hydrogen. And we denote that by how many carbons they have by meth, eth, prop, but, penta, etc. That's how many carbons we have. If we want to use that chain as to be on a compound as a substituent, or basically something we don't care about when we only care about the functional group, we want to change the name to have the YL in it, methyl, ethyl, propyl. That's telling you that that alkane chain is a substituent on something bigger. So that's what this little thing means here, is that there's something bigger, but there's a sigma bond between this carbon and whatever else there is here. Okay, that's what we're denoting by this. So we know that that is a substituent because of that YL. If we were just talking about the hydrocarbon itself, it would have the ANE at the end of it. One carbon, meth, ANE, hydrocarbon. But by making it bonded to something else, that one carbon bonded to something else, we now have the methyl substituent. And that works for all the other kinds too. If we have the ethane, break that bond, put a functional group here, we now have the ethyl substituent. And it works for every hydrocarbon. So you can have icosane, which is 20, and you can have the icosyl substituent. It doesn't matter how many carbons you have, but you add that YL, it turns into a substituent and shows you what's bonded to it. Okay. Do we understand the line drawing here then? This just means the other part of the molecule, and that these two atoms are the substituent, ethyl. These three atoms are the substituent. These four atoms are the substituent. Do we see how that works? Okay. So if we move from there, let's talk about our functional groups. Okay. We have a couple different types of functional groups. One of them can contain just sigma bonds, but then some of them contain pi bonds too. Okay. So let's talk about some of the basic heteroatoms that we're going to do first. We're going to have, first of all, sigma bonds, because they're first to start with, they're single bonds. So we can have those with carbon and nitrogen, oxygen, Let's see, fluorine, chlorine, sulfur, phosphorus, any of these. So a carbon bond to anything, any of these atoms, heteroatoms, atoms other than carbon, they all have polar bonds to some extent, right? Because even carbon and nitrogen have a difference in electronegativity, giving it a polar bond. So that's one of those things that's interesting about that. Now we can go the other way and go with boron too. It's the other way, okay? But boron's going to be a little different. Now, if we look at that carbon with the heteroatom, let's say oxygen, which is more electrophilic, oxygen or carbon? Oxygen. So that means we're going to have a polar bond that's going to go in the direction of oxygen. Because oxygen wants the electrons, it's going to draw the electrons toward it, giving us that polar bond, partially positive charge on carbon. What about boron carbon? Where is it on the periodic table? Which one's more electronegative? Carbon. So that means we're going to have the positive charge on the boron, not the carbon. So most of the time it will be on the carbon, but when you have carbon as the most electronegative atom, it's going to carry the electrons. It's going to pull the electrons toward it. Okay, so that means you can take any element on the table and know which direction that dipole is going to go. Interesting. And because you know whether your atom, your carbon atom, is partially positive or partially negative, that means you're going to get an idea of what can react with it. If it's partially positive, something negative or partially negative wants to react with it. If it's partially negative, something positive is going to want to react with it. So knowing that it's polar, knowing which side is positive will tell you how to look at the structure. Even if you've never seen the structure before, you can say, well, this is the positive side. That's got to be the part that has to react with the negative ion. So you can really deduce from just that thing where to go, even if you've never seen the thing before. Okay, so then when we talk about these groups, we also have to include that it can be, or our group can represent any alkane or alkyne, because again, those are just carbon-carbon bonds, and those count, hydrocarbons count, or the aromatic compounds, or their arenes. In the case of an aromatic group right here, like the benzene ring we talked about already, we typically use it as the pH or occasionally AR in that line. That line is the bond to whatever the functional group is. Okay, so this bond is to whatever our functional group is. And so R can be any of those alkanes, those hydrocarbons, but AR and pH tend to be used with the aromatic hydrocarbon. Okay, can you have more than one functional group on a compound? Yes. And then you'll have to see which one's going to be more reactive, but we'll talk about that later. Okay, so let's talk about some of the basic functional groups. And these are functional groups that we will need to know for our quiz on Monday. So that might be something to study. And what I'd like to show is two different examples. One is the general structure here. And when I draw the general structure, I'd like you to have the lone pairs on there for right now. You got to get used to knowing those lone pairs are there because it tells you shape, it tells you reactivity, it tells you stuff like that, okay? And then I go through them each. So if we just had a hydrocarbon, they're just going to be alkanes, right? Or alkenes or alkynes. And so they have no functional group. But if we take one of those hydrogens off and replace it with any of the halogens, fluorine, chlorine, bromine, or iodine, then we've turned into an alkyl halide. So they're halogens, they're halides, they're alkyl halides, or aryl halides, okay? And that general structure would just be like this methyl bromide here. And notice the lone pairs are there to show us that it's there. And we call that functional group the halo group. It's not a bunch of guys running around with electronic guns. It is the halogens bonded to a hydrocarbon. Okay, so it's the halo group or alkyl halide. Come on, there we go. And so it's alkyl halide. Now, if we take that off and put a different heteroatom on here, so we started on this side, we started on row 7, let's go to row 6, we have oxygen. Now notice that our row 7, our halides here, have 7 electrons in their outer shell, so they need to bond once. So there's one bond to carbon. When we move over to oxygen, it has 6 valence electrons. It needs to bond twice, but it's going to have 2 lone pairs. So look at our structure here. We've bonded an oxygen to a carbon, and we bonded the oxygen and hydrogen. So in an alcohol, we have carbon, oxygen, hydrogen. And we call those alcohols. Okay. And we have to have a carbon, oxygen, hydrogen bond. And that general structure is here. And notice those lone pairs again. Those lone pairs give us something about reactivity and maybe polarity and maybe solubility. So we have to pay attention. And we call that the hydroxyl group. Hy for hydrogen, ox for oxygen, hydroxyl group. Boom. All right. If we change that just a little bit, and instead of having that carbon, oxygen, hydrogen bond, we change it to a carbon, oxygen, carbon bond. Number one, oxygen has 8 electrons around it. It's happy, but it has 2 carbon bonds. It's changed functionality again. And we call that an ether. Okay. And in ester, we have the ether bond. It's 2 R groups on an oxygen. Anyway, so when we look at that, look, it's got lone pairs again. We're going to be able to use those to do some kind of bonding, maybe an interaction there. Yes.
So are those R carbon chains? Are they still alkyl groups? Because
they can, any alkyl group. That's why we call this a general structure. It can be any alkyl group.
okay.
And for space, we use methyl groups here.
Okay.
Okay. But, and so that's another thing about it is that you don't have to get all bogged down and, oh, that's a hexyl chain with 7 things on it. Well, no, that's the functional group. It's an ether, just by looking at the carbon, oxygen, carbon. So you're looking for that substructure tells you your functional group. Okay, good question. All right. So let's go on again. So now we've done column 7, we've done column 6. Now let's go to column 5, and we're going to go nitrogen. Nitrogen has 5 valence electrons. It wants to bond 3 times and have 1 lone pair. But nitrogen can be a little different. Okay, so if we just have 1 carbon nitrogen bond right here, 1 carbon nitrogen bond, that makes it an amine, A-M-I-N-E. Okay, we're going to have another functional group that changes that name slightly. A-M-I-N-E. So now, because nitrogen can bond up to 3 times, because it has 5 valence electrons, that means that you can have 1 carbon nitrogen bond, or 2 carbon nitrogen bonds, or 3 carbon nitrogen bonds. As long as there's 1 carbon nitrogen bond, it's an amine. Okay, so that's why we have 3 different structures here. We can have 1 R group, 2 bonds to carbon, 3 bonds to carbon. And that just gives us this. And again, this is slightly less polar than these bonds here because it's slightly closer to carbon. So let's instead go down 1. So we're going to go down 6 and look at sulfur. And if we look at sulfur here, we have 6 valence electrons. It can have 8, but it can also have 10. So in this case, we have 8. And so we have 2 lone pairs and 2 bonds. And in this case, we have a carbon sulfur hydrogen bond. And we call that the thiol group. Okay, the thiol group. Okay. So, but as a substituent, we have a slightly different name. So the OH group, the alcohol group as a substituent was the hydroxy group. When we changed it to the ether, this whole thing becomes the alkoxy group. Oxy for oxygen, al for alkane. Alkoxy group. When we changed it to the nitrogen, we call that the amino group. Amino group. When we go to the thiol, we call it something really weird. We call it mercapto. And that comes from older, like literally, I think it comes from alchemy, mercapto, and they tend to be very smelly things. But the substructure here is carbon, sulfur, hydrogen. Okay. And then if we do just like in this case here, where we do an ether, we do a carbon, sulfur, carbon, we now change it to a sulfide, also called a Thio Ether, because it's the sulfur derivative of ether. And we call those sulfides, and that is also called the alkyl thio group. Just like here, the alkyl group and the thiol group make it a substituent. Okay, So we see the different classes, the different general structures that are important, and their substituent name. Okay, so that's going to be important. So let's talk about getting a little more specific about where things are. Okay, so if you have a carbon bonded to only one carbon, we have a special class for that. We call them primary carbons. So carbon attached to only one other carbon is a primary carbon. If we have a carbon attached to two other carbons, we call that a secondary carbon. So you're looking for the number of carbon-carbon bonds. So of course, 3 is tertiary, and then 4 is quaternary. Okay, so let's look at these structures down here and look at where we have different primary and secondary hydrogens. So this carbon right here, is it a primary or secondary or tertiary or quaternary carbon? Primary, because it's only bonded to one. So what's the one next to it then? Secondary, because it's bonded to. So you should be able to recognize this in this condensed form. What if I drew it like this? What's this one? Primary, because that bond is just bonding to one. So what's that one? So what's that one? And then, so we can just see how many carbons are touched there, and especially in the skeletal form, it's very easy to see primary, secondary, tertiary, and quaternary. Okay, so when we move on to different structures, even in these extended structures, like in these condensed structures, you can tell that there are 4 carbons here, so it's a quaternary carbon. Okay, so that's how we identify carbons. But how do we identify the hydrogens that are on those carbons? Okay, the way we identify them is to say what kind of carbon it is and tell you it's the hydrogen's on there. So a primary hydrogen is a hydrogen on a primary carbon, which makes a secondary hydrogen on a secondary carbon and a tertiary hydrogen on a tertiary carbon. Okay, so do we have quaternary hydrogen? No, because all 4 bonds are taken up by carbon. Therefore, we do not have quaternary hydrogens. So we can only have primary, secondary, and tertiary hydrogens, which makes these primary hydrogens because it's on a primary carbon, which makes these secondary hydrogens because they're on a secondary carbon. And then on this tertiary one, we got to remember there's that 4th bond there. We don't draw it there because it's hydrogen, but we got to remember it's there because that's our tertiary hydrogen. Okay, questions on primary, secondary, tertiary carbons or hydrogens? Okay, so we follow that along when we have other groups attached to it too. So when we have an OH group attached to a carbon, we can say that that is a primary, secondary, or tertiary alcohol based on the carbon. So if we have this structure here, right here, what is this alcohol now? Just from that description. That alcohol is hooked to what kind of carbon? Quaternary would be 4 bonds to carbon. There are 3 bonds to carbon, 1 to oxygen, which is our heteroatom. So it's a tertiary carbon. So that makes it a tertiary alcohol. The alcohol is on a tertiary carbon, therefore it's a tertiary alcohol. So what does that make this one? Secondary, and then of course our last one is primary. So that works for any alcohol, or if we want to change our structure up even crazier, a fluorine, a chlorine, and an iodine here, those alkyl halides are going to follow that same structure. The iodine is on a primary carbon, so it's primary. The chlorine is on a secondary carbon, so it's a secondary chloride. The fluorine is on, that should be a tertiary carbon. Okay. The fluorine is on a tertiary carbon, making it a tertiary fluoride. Okay, so we see how that classification works. So up to now, it's what the carbon is, and that defines the alkyl group, that defines the hydrogen, that defines the alcohol, and that defines the halogen. So we can tell our primary, secondary, and tertiary halogens, hydrogens, and alcohols by looking at the carbon. Okay. Now I want to break a rule. Amines are backwards. I said amines are any structure where you have at least one carbon-nitrogen bond. So if you have one carbon-nitrogen bond, that means your other two bonds are going to be to hydrogen, and that makes it a primary amine. In the case of amines, it's how many carbons are bonded to nitrogen. Okay, which means that if we change it to this, this becomes a secondary amine. And if we put the 3 bonds to carbon with 3 different ethyl groups here, let's draw our lone pair just to make sure we know they're there. That is going to be our tertiary amine. So amines are backwards, but alcohols, hydrogens, and halogens all depend on what the carbon is. Amines depend on how many carbons you have bound to the nitrogen. All right, does that make sense? It's the one weird thing, but it's the only one. So if you follow the rules, it'll be fine. Okay, so that being said, we can look at this and go to, so that's our first set of functional groups we want to go. Those are our basic functional groups. Notice those all had sigma bonds, okay? Those all had sigma bonds. So I want to change to a functional group that doesn't have a sigma bond. Well, it does have a sigma bond, but it also has a pi bond. So the next functional group I want to talk about is the carbonyl, which is the C double bond O. So I'm going to draw it here, C double bond O. I'm going to put lone pairs over here. And usually there's 2 other things bonded to this. So I'm just going to put R's here just to show you that that carbonyl there. So first and foremost, what is the hybridization of the carbon in this structure? You should be able to tell by its shape and its number of bonds. sp2, because we have a sigma bond here and a pi bond here. And if we have a pi bond, that means we must have an unhybridized p. We have 3 sigma bonds, so that means we have 3 hybridized orbitals, sp2. 3 hybridized orbitals, sp2, trigonal planar. So we have a trigonal planar. So we have sp2 hybridized carbon. Oops, 2. What's the hybridization on oxygen? It has a sigma bond and a pi bond and 2 lone pairs. It's also sp2. It had to have an unhybridized p to make the pi bond. And if you look at it, these lone pairs make it trigonal planar. So that oxygen is also sp2, and we can see that by the shape. Okay. So the other thing about this is oxygen is more electronegative than carbon, therefore it's polar. I'm sorry. It's pulling electron density away from the carbon toward the oxygen. So now we know where things are going to react. Something positive coming in is going to react with the oxygen. Something negative coming in is going to react with the carbon because of that polarity. Okay. And we see that that bond, that pi bond, is the one that's going to break first. You have to break that pi bond first. It's more reactive. Just like when you have an alkene, the pi bond breaks first and then the sigma bond. We're going to see that happen. So if we look at that as a polar compound with our lone pairs here and our carbon down here, this carbon is partially positive. This oxygen is partially negative. Now we can actually draw a resonance structure of this because remember, resonance structures, we can move electrons, we can move pi bonds, but we can't move any of the other atoms. If we do that, we have carbon here, oxygen with 3 lone pairs up here now. This lone pair went up here, giving us a full negative charge here and a full positive charge here. And this is in resonance, double-ended arrow, resonance, okay? Which of these is more stable? The one with the 2 charges or the one with the partial charges? partial charges because this carbon does not have a full octet. That carbon does not have a full octet, it's less stable, but it's still in resonance. And because this is a valid resonance structure, even though it's less stable, it tells us there's a positive charge on carbon, which gives us our partially positive charge on carbon all the time. Okay, does that make sense? So this carbonyl is the beginning of a whole other set of functional groups. Our first set we talked about were all sigma bonds. This all involves the carbonyl. So the first functional group we want to talk about with our carbonyl is called the aldehyde. Okay, this is a carbonyl with at least one hydrogen bond. Okay, that's the defining factor. C, double bond O, hydrogen. So carbonyl to a hydrogen. Now, we do have one structure that has two hydrogens on it. This is the simplest aldehyde. We call it formaldehyde. Okay, and it still has a partially positive charge here and a partially negative charge here. But most of the time, we want to have some kind of R group on there. So that's the general structure. But the key feature is it has to have at least one hydrogen on there. Okay, and if we draw it out with our example here, we see that that has it. So we call these aldehydes, and we're going to change the name when we do that. But the key feature of this is our carbonyl as the functional group. And what's attached to the carbonyl changes the name. Okay, let's take away that hydrogen and only have carbon bonds to that carbonyl. So we have two carbon bonds to that carbonyl. It's still sp2, it's still planar, it's still partially positive, but we've changed the name. This hydrogen reacts differently than this carbon would, therefore it changes the name, it changes reactivity. We call it a ketone. So carbon, carbonyl, carbon, ketone. Carbon, carbonyl, hydrogen, aldehyde, carbonyl, carbon, carbonyl, carbon, ketone. Okay, so that's going to be the first way to do it. And so we've basically taken our carbonyl and done carbon and hydrogen, just like it was a regular hydrocarbon. Now let's start inserting heteroatoms. The first one we're going to do is oxygen, and we're going to do it kind of like we did with the alcohol, where we had our carbonyl, but we have an oxygen bonded to a hydrogen. This structure is called the carboxylic acid. Okay, carboxylic acid. And the reason we say that is that we're going to find out in another chapter here that this hydrogen can be acidic and actually be taken away by bases. Okay, so we're going to call this the carboxylic acid. So think about it, carbonyl plus an alcohol equals carboxylic acid. Okay, and so we'll see that that still has the carboxyl group as a whole is our functional group. C double bond O, COH. That is the functional group, the carboxylic acid group. Okay, now let's take the hydrogen off. Just like we did when we went from alcohols to ethers, we're going to go with a carbonyl bonded to an oxygen, bonded to another carbon. So see how it's changed. We moved the hydrogen away, we added a carbon. It changes functionality. It's no longer acidic. So we changed the name and it's now called an ester. Okay, and so the functional group is this carbonyl, which is COOR. So that's the general structure there. So we've done our two oxygen derivatives. Now let's do a nitrogen derivative. So the nitrogen derivative, we'll start with, we have a carbonyl nitrogen bond. Okay, a carbonyl nitrogen bond turns it into an amide. Carbon single bonded to nitrogen was amine, A-M-I-N-E. A carbonyl bonded to a nitrogen is amide, A-M-I-D-E. Okay, amine, amide, amine, amide. Okay, so that's a big difference between there. And we can have hydrogens or alkyl groups here, and that's going to change how we name it. And we call that the substructure here with, it has an oxygen and a nitrogen, and it has that carbonyl functionality. Now, what if we take this oxygen off and turn it into something even more acidic, more electronegative and put a chlorine there. So chlorine's more electronegative than oxygen. And that makes this even polar bond. Now, technically, we could put any halogen there, but most of them aren't very stable. This is probably the most stable of this carbonyl halogen. And so we typically call it the acid chloride. Because it was a carboxylic acid, we took the OH off and put a chlorine there. So we call it the acid chloride. But the key feature there is that we have a carbonyl bonded to a heteroatom and a very electronegative heteroatom at that. Okay, questions about that?
So if you had like a fluorine bonded in place of a
It would be an alkyl fluoride.
not,
I'm sorry, acid fluoride.
okay,
Sorry, yes, acid fluoride. If it has a carbonyl that's bonded to a halogen, it's going to be acid, whatever the halogen, acid bromide, acid iodide, acid chloride is the most common. Okay, so, and that's denoted by this little structure here. So this is like the condensed form, how you'll see it written in the book sometimes. This is how we'll draw it out. And of course, in stick figures, you'll just be looking for your double bonds and your atoms labeled correctly. Okay, so now I want to take you and show you one other derivative. And I want to show you that it's a derivative of this right here. Now that structure, okay, yes, question. Oh, I have a question. Let's see. Does R stand for CH3? In this case here, R can stand for any alkyl group. However, in this example here, R is the methyl group, yes. But this is the general form that we can have any R group, and that'll still be the same functional group. This is just an example with methyl as the substituent. Okay? Thank you. All right. So I want to tell you that this right here makes one more functional group, and it's technically not a carbonyl compound anymore. It's a nitrile. So let's draw that out. We have R, C, triple bond nitrogen, but there's still a lone pair there. Okay, so we still have a lone pair. So that is going to tell us something interesting about that compound. But I said it is part of this. Well, if we take this and we redraw the amide, hydrogen, hydrogen, right here, and of course there's a lone pair, and we remove the oxygen and two hydrogens, that's going to give us water, right? Move those two hydrogens and then oxygen gives us water, and that moves this double bond in here. I'm sorry, this double bond here, and leaves our lone pair, and we end up with our nitrile. So our nitrile is technically a derivative of our amide, but it gives us that new functionality, that C triple bond N. And unlike the C triple bond C, it's polar, and it has different functionality than the acetylene has. Questions on that? So quick, how many sigma bonds and pi bonds do we have between that nitrogen and that carbon? 1 sigma, 2 pi. Perfect. So always recognize that you have 2 pi's, which means you have 2 p orbitals unhybridized, which means what's the hybridization on carbon? sp. And the hybridization on nitrogen? sp, which means these lone pairs stick out 180 degrees from that initial sigma bond. Ooh, we can see everything about the structure, the polarity, and the shape by paying attention to p's, sigmas, and pi's. All right, questions on that? Okay, so let's move on to looking at an overview of what we just talked about. So the hydrocarbons have 4 things in them: alkanes, sp3 hybridized carbons only. All right, so sp3 only, alkanes. We have at least 2 sp2 hybridized in alkenes. Okay, we have at least 2 sp hybridized in an alkyne. So we have only sigma bonds. We have a sigma and a pi bond, and we have a sigma and 2 pi bonds. right here. So those are our basic hydrocarbons, okay? The last member of our hydrocarbon family is our aromatics, and that was the alternating single and double bonds that don't react like single bonds and they don't react like double bonds. So we're going to talk about them separately next semester. But this group is part of the hydrocarbons because it only contains hydrogen and carbon. Then we started adding things to it. We started adding things from group 7 first, which is our halogens. And we have 3 lone pairs and a single carbon halogen bond. And that single carbon halogen bond is always polar. Okay. And so we can have a number of different ways to do that. And we'll talk about the names and the common names in chapter 4. So, but I just wanted to show you that those are the classifications. This is what we're looking for. We're looking for instant identification of functional group and hybridization by looking at the structure. That's what you want to study for. You want to say, oh, if I see something that looks like this, it's probably an alcohol. Okay, so now we switched it over to oxygen, moved over one. Oxygen with a hydrogen, alcohol. Oxygen with a hydrogen, alcohol. Oxygen without a hydrogen, oxygen with 2 carbon bonds, ether. So again, it's carbon, oxygen, hydrogen, carbon, oxygen, carbon, differentiating between those two. Okay, then we go to the carbonyl section plus the amine section. So the first thing we learned about amines is it's the carbon nitrogen bond. It's polar covalent, and it's an amine, and it has that lone pair on nitrogen. Because it had 5 electrons, only needed to bond 3 times to get its full octet. But our next thing was our cool double bond carbonyl. Carbon oxygen with a sigma and a pi bond, giving us this functionality. And the carbonyl hydrogen is our aldehyde. The carbonyl with 2 carbon bonds to it is our ketone. Okay, so that's kind of like the hydrocarbony derivatives of the carbonyl. Carbonyl hydrogen, aldehyde, carbonyl, carbon only, ketone. Then we switch to having our groups that were more electronegative. Okay. So with just an OH on there, kind of like COH was an alcohol, carbonyl OH is the carboxylic acid. So look at it for that structure, look for that kind of structure. Then if we get rid of that hydrogen and replace it with a methyl group here, or any alkyl group there, it changes functionality. Again, it's no longer an acid, so it's an ester. So it went from a carboxylic acid to an ester. And then by adding nitrogens to them, instead of oxygens, we got to the amides. Amides have a carbonyl. So carbonyl bond to a nitrogen is AMIDE, amide, no pi bonds, amine, AMINE. And then, of course, the last one is our C triple bond N, our nitrile. Questions on that? Okay. Now, looking ahead, are the bond strengths of sigma, pi, and 2 pi bonds and 3 pi bonds, do they all have the same energy? No, they don't have the same energies. And I'm going to prove that to you when we start talking about IR. Okay, so let's move on and get your phones out and do your Bobcat trace. At home, you don't have to, you can, but if I have you in the participants form anyway, so either one is fine. Okay, so while you're doing that, for the quiz, I would do like flashcards just looking at a generalized structure. You want to identify the generalized structure to the different functional groups. And it's good to do it now because we're going to be using them all the way through the semester. We might not be making some of them until next semester. We're going to go all the way up to alcohols this semester. But being familiar with them because we're going to use them as solvents, we're going to use them as names and stuff. So it's really important. Okay, so everybody's phone seems to be down, so I'm going to move on to intermolecular forces. So in our bonds, I wanted you to notice whether or not they were polar or not, right? So because bonds can be polar or not, molecules can be polar or not, right? If they all cancel out, they're non-polar. If they don't cancel out, the molecule itself is polar. So what does that matter? Well, when this molecule comes up close to this molecule in space or in a liquid, how are they going to interact? They both have clouds of electrons on the outside, so they want to repel each other, right? Well, we're not living in a gaseous state where they're all repelling each other. There must be something holding them together. There must be something allowing them to get close together. And that's what we call our intermolecular interactions. That's molecular interactions between two things. If it's an intra with an A, intramolecular, that's a molecule reacting somewhere on itself. So we're talking about two different molecules and how they come together, okay? So when we're talking about these interactions, to get our molecules to even come together, there has to be something to overcome that electron-electron repulsion, okay? And so we have several different forces that allow us to do that. And we're going to start with our weakest forces and go to our strongest forces. Our weakest forces are what we call induced dipole, induced dipole. So imagine you don't have a dipole yet, but as you squeeze things together, you'll say, okay, I'll kind of force a dipole to happen and I'll get some kind of interaction. So that's one way to do it. And then if our molecule already has a dipole, it already is a polar molecule, it's going to have a partially positive side and partially negative side. That means that partially positive side is going to come up next to the partially negative side of the next one. And the next one's going to come up to that, the other partially charged side. So they can stack together. And that's stronger than forcing it to have a dipole. So it's a slightly stronger bond. So we have forcing it to have a dipole. It already has a dipole. That's good. But we even have a stronger force, and it's hydrogen bonding. Hydrogen bonding is where those acidic hydrogens, those hydrogens like on alcohols and carboxylic acids, will start to bond to neighboring lone pairs. And they can do it once, twice, maybe even 3 times. And that's an even stronger bond. So we're going to talk about that. The next bond we have are actually our covalent bonds. That's our next strongest. And then we have ionic bonds. So I want to discuss all of those in order. We're going to start with our weakest, which is induced dipole, and go all the way to ionic. Okay. So these intermolecular forces are kind of important because it tells us, number one, will this dissolve in this? If they have similar interactions, they might dissolve. Where will this melt? If it has very poor interactions, it's going to melt very low. If it has very strong interactions, it's going to melt very high or boil very high. Okay, so we need to pay attention to that. So in an induced dipole system, imagine you have a hexane over here and a hexane over here. And they're floating around in solution. They're starting to come next to each other. This is completely nonpolar. This is completely nonpolar. But as they get together, one of them says, okay, I'll move some of my electron density to the one side of the molecule. And then because of that, the molecule next to it says, hey, this side of the molecule that I'm coming up next to is slightly positive. I can move some of my electrons onto that side and become partially negative. And so it's inducing a dipole and they can stack together. So if we look at that in this section here with these pentanes here, so we're getting a little bit of negative over here. And I'll denote that as this red section here. And that means the other side is slightly positive because those electrons have been moved to this side, right? Now the neighboring molecule wants the opposite charge to be attracted to that side of the molecule. Okay, so partially negative side of this molecule is going to stick to the partially positive side of that molecule. Okay, so this is a weak interaction because you have to force it to have a dipole. But there's 2 things that'll govern it. Number 1, surface area and molecular shape. So why would surface area matter? Well, in the case of this pentane, we can do multiple sections where we have that partial charge formed, right? We have a whole bunch of different atoms, a whole bunch of different hydrogens that are on the outside of that molecule that can start coming together. So we can make teeny tiny little bonds, a bunch of them all the way along the system, along the chain. What if we had 2 molecules that were more spherical? They still had the same number of atoms. As they get closer together, only 2 or 3 of the hydrogens are close together. we can only afford 2 or 3 of those induced dipoles. Which one's going to have the lower melting point and boiling point? The one with the fewer interactions. So the fewer the interactions you have, the lower your melting point and boiling point are, because there's less things holding you together. So in the case of our pentane here, pentane actually boils at 50 degree, 35, 53, 50, no, 35 degrees. It's barely above room temperature. But the isopentane actually boils lower. Okay? Not because of its size. They're both 5 atoms. There's actually a weaker induced dipole interaction because there's fewer of them. It's a weaker induced dipole interaction, and therefore it has a lower melting point and boiling. Okay, so what we can say from this is most of our hydrocarbons only have this kind of interaction, this induced dipole, because they don't have dipoles. So when we see hydrocarbons and alkenes, alkynes, and aromatics, we typically see this kind of interaction. Okay, so then our next stronger one would be something that instead of having to force it to have a dipole, it has a permanent dipole. So if we look at things like this right here, this acetone carbonyl, we know that this is the partially positive side of the carbonyl, and this is the partially negative side there, and it's always there. So that means when that partially positive side gets attracted to a molecule, it's going to be attracted to the partially negative side of the molecule near it. And we can stack those up, positive, negative, positive, negative, positive, negative. Okay. So it's only one interaction, but it's a stronger interaction, or it's one interaction per side. Notice there's going to be an interaction on the positive side and the negative side, but it's a stronger interaction. And therefore it's going to have a higher effect on melting point and boiling. So we can actually have another weird one where we have a dipole interacting with an ion, but it's a little different in the fact that you still have the dipole, and your dipole has a partially positive or partially negative charge. Therefore, you can't just have one molecule that's partially positive completely counterbalance all the negative charge of the full ion. So what you do is you put multiple little teeny forces around it in what we call a solvent shell, where we have this hydrogen is partially solubilizing it, this hydrogen is partially solubilizing it. So all these partial ones go all together. So each one of these waters carries 1/6 of that charge. It's sharing that whole negative charge between all 6 molecules. Okay, so that's how we can get things like ions into polar compounds. Even though they're not a full an ionic bond in the liquid state, we have this kind of interaction that allows us to do that. Okay, so we have induced dipole, we have dipole, we have dipole ion as a special subset. Now let's talk about hydrogen bonding. Okay, if you have a polar bond between hydrogen and an atom, you can have hydrogen bonding. But we're only going to say that we have hydrogen bonding between nitrogen, hydrogen, oxygen, hydrogen, and fluorine and hydrogen. It's rare, but it happens. Now, why do I say we're going to talk about oxygen and nitrogen only? Those are the ones that give us a polar bond with hydrogen. Sulfur, one group down, is the difference in electronegativity between sulfur and hydrogen is not big enough. It's not hydrogen bonding. Carbon, it's the difference between the carbon and the hydrogen is not polar enough. It's not hydrogen bonding. So the only ones that can are nitrogen, oxygen, and fluorine. Yes. Can, yeah. Fluorine, hydrogen, the hydrogen on a fluorine can hydrogen bond. But when we talk about it here, it's almost always hydrogen on a nitrogen or hydrogen on an oxygen. Now, think about a couple of functional groups then. We have alcohols that have the COH. Then we have carboxylic acids, carbonyl OH, both of those hydrogen bonds. We have 2 nitrogen containing ones, the amine CN, and if there's an H there, that H can hydrogen bond. And in the amide, those H's can hydrogen bond too, but a little bit weaker. So anytime you have an oxygen hydrogen or a nitrogen hydrogen, you have an opportunity for hydrogen bonding. So what is hydrogen bonding? Well, the fact is that that bond, because it's polar, means the hydrogen side is partially positive. And this side is the partially negative side. But also, nitrogen has one lone pair on it, oxygen has two lone pairs on it, which means that that hydrogen can be attracted to the lone pair on this side, and another one can be attracted to the lone pair on the other side. Those partially positive hydrogens are attracted to the lone pairs on the oxygen or nitrogen that's neighboring. Okay, so that are on adjacent molecules. So not only do you have, number one, a stronger interaction than a dipole-dipole, you have more of them available. One hydrogen can hydrogen bond to one or two different lone pairs. Therefore, it has more interactions and has more of an effect on the boiling point of milk. All right, does that make sense? It's stronger, it's the next thing up. So then we have our effects that we have. So melting, by definition, is just getting the things to go from a rigid state where they can only just vibrate to start slipping past each other. So that means whatever it takes to break that, that whatever that crystal packing is, whatever that order is, it takes to move it. Boiling, on the other hand, is breaking all intermolecular interactions. Melting, you're only going from a rigid state to its liquid molecular interactions. Boiling, you're going from liquid molecular reactions to no interactions. So there's always a larger effect. There's typically a larger effect on the boiling point. Okay, so let's look at ethane. Ethane is a hydrocarbon. Therefore, what's the only kind of bonding it can do? Induced dipole. So it's the weakest energy, and we have a very low boiling point and a very low melting point. And it only has that induced dipole. Just by adding one little bit of a polar bond, by adding this chlorine bond here, we have increased the melting point and we've increased the boiling point right here, almost 100 degrees. Now, is this an apples to apples comparison? Not exactly, because molecular weight also changes boiling point, melting point. The higher molecular weight you get, they don't, but just adding a polar group does affect it that much, even though we're not exactly the same molecular. I'll show you a comparison with exact molecular. By going to a different kind of polar group, in this case, an aldehyde, it's carbonyl. Right here, we see again, it increases the melting point and the boiling point right here. And that's a dipole-dipole interaction on both of these cases. Now, we've gone from induced dipole to dipole-dipole. Now let's do some hydrogen bonding. Let's start with an alcohol right here. Our melting point here doesn't change all that much, but our boiling point shoots up 150 degrees. Oh, no, I'm sorry, that's 90. Yeah, it's like 100 degrees above that induced dipole. And that's all because of hydrogen bonding. Now let's go to a carboxylic acid, which has a more acidic hydrogen. It's going to more strongly hydrogen bond, and it goes up again, both boiling and melting point go up. Now, what if we go and take all the hydrogen bonding out and go to that next strongest one, which is a dipole ion interaction? Well, the melting point definitely goes up, and then it's so strong that it'll actually decompose before it volatilizes in the air. Okay, so that's saying that that ionic bond is stronger than our covalent bonds or any of these other interactions. Okay, so that's the order of strength in those structures. Okay, so why does it affect? Yes.
I asked that when induced dipole, that's by like the randomness in which electrons move in electron file, right?
It's more like, let's say, so your shells of electrons right? They can be anywhere in that three-dimensional space, right? And when we start to shove two of them together, this one's going to spend more time on this side, giving it slightly more negative charge, and less time on this side, giving it slightly less negative charge. So this is, in comparison, partially positive. The one coming next to it is going to shift, its more electron time is on this side. So it's more negative than this side. And so this less negative side and this more negative side are going to attract each other. That's induced dipole, induced dipole. Okay, so imagine you just have that, you know, in the simplest state, you take that S spherical orbital and it spends more time, the electron spends more time on the side away from the incoming molecule. And the one coming in has more electrons on that side, so that partially positive and the partially negative are coming close together. So they can be closer together than just two negative balls put together. Okay? So I hope that actually probably clarifies a lot of things. All right, so let's talk about boiling point. So boiling point, it definitely has a bigger effect on boiling point than on melting point because of the breaking all intermolecular interactions. We have to go from like things moving past each other to breaking all of them to get into air. It's not dissolving in air, it's just broken all its molecular bonds with the solvent itself, and it's coming out into the gaseous phase. So that's why it has a greater effect on it than than melting here. And an example of that would give us things like, well, if we have induced dipole, induced dipole, induced dipole, okay, those are probably pretty easy to break up because there's no permanent dipole. So it's easier to break those intermolecular interactions to get them to boil, right? And then if we go up to a slightly stronger one, the dipole-dipole interaction, well, you know, it's just one side of the molecule attached to one side of another molecule, and those can break two of them and then they'll be up in there. So that should be a little higher boiling. But then let's go to hydrogen bonding, where it can be hydrogen bonded to two or more different lone pairs. It has to break every single one of those lone pairs, and you have to break all the hydrogen bonds to the oxygen or nitrogen that has the hydrogens on it. So that's 3, 4, 5 interactions it has to break. So it's higher still. So just looking at this, it increases the effect on boiling point because the number and strength of the interactions you have. Okay, so for example, all the same molecular weight, if we had pentane, we're going to see that it boils at 36 degrees. If we change that to an aldehyde, right here, this has approximately the same molecular weight. It has a boiling point of 76 degrees. And then let's change it to something that has hydrogen bonding. And so I actually have to lose a carbon because I'm adding another oxygen to give it a hydrogen bonding. So this is a carboxylic acid, and this boils at 100. Oh, I'm sorry, not that. Let's do butanol, which is an alcohol of butane. It has the same molecular weight, and it has a boiling point of 118 degrees. Okay, induced dipole. These all have plus or minus 2 molecular weight units, the same molecular weight. Induced dipole, dipole, hydrogen bonding. Significant difference in the boiling points. All right, we see that trend. All right, so when we have that, there's a couple other factors that will affect boiling point. The two big ones are molecular weight and interactions. Those are the two big ones. The two minor ones that also come into play are surface area and symmetry. So if we think about dipole-dipole interaction, I said if you have big long chains, you're going to want to have more of the surface area together to have more of the little teeny interactions, and it'll have a greater effect. So surface area will increase our boiling point as well. And then symmetry. Symmetry is if, let's say we had, instead of the hexanes, we have a pentane with a methyl group hanging off of it. that methyl group is going to act like a thorn in its side. You can't get another molecule. It has to go just on the right side to get close to it. So symmetry has that effect. So that surface area and symmetry run hand in hand in giving us that secondary effect on boiling. The last thing we want to look at is polarizability. The more polarizable the bond is, the more of an effect it'll have on boiling. And we think about that, if it's big and has a lot of electrons around it, not only do we already have a permanent dipole, but we can influence that dipole by saying, hey, it's a big weak bond, it's a long bond, it's a big atom. I can pull some more electron density. You can almost induce an extra dipole, an extra amount of that bond. So the more polarizable the molecule is, the more it will enhance the boiling point of your compound. Okay, so the big two are intermolecular interactions and molecular weight, followed by surface area and symmetry and polarizability. Yes.
Is that one of the reasons why really big elements, like big elements, they're so unstable and radioactive?
That has to do with the nuclear stability. Radioactive has everything to do with about the nucleus.
Okay.
We're just talking about electrons. That's a whole other ball of wax. I do teach that class, but not here. Okay. Anyway, so let's talk about melting point. Melting point is a little bit different. Because we have everything kind of has to, number one, has to stack together just right in a very regular pattern. Symmetry is more important in our melting point than it was in our boiling point. Because if you have stuff that is like they can stack up this way, but they can't stack that way. If they have a symmetrical element, they have to wait around and stack just right. Okay, so we have a symmetry as a problem here. And it doesn't have as dramatic an effect on melting point as boiling point, because in our symmetrical crystal, we have those intermolecular reactions. They're just not moving past each other. In our liquid, we have those intermolecular reactions. They're just moving past each other. So what you're doing is you're breaking up the order. That's your melting point. You're breaking up the order. So symmetry becomes a element there. The more symmetrical, the more they can pack, the higher the melting point. The less symmetrical, the harder it is to pack, the lower the melting. But once it gets into the liquid, it's all about those other intermolecular interactions. You have to completely break up to boil them off. Questions on that? So you'll see a melting point and boiling point trend on shape, polarizability, molecular weight, and intermolecular interaction. Okay, okay, no questions? And all right, 12 minutes. Excellent. All right, so let's talk about solubility. Solubility runs hand in hand with our different types of intermolecular interactions. If you have all the same thing and you have dipole-dipole interactions and you put it into something else, what kind of interaction do you think it wants? Does it want a non-polar interaction? Does it want an induced dipole interaction? Probably not. It wants to have the same type of interaction. So we have a common thing of this is that when we have a solvent and we're trying to dissolve something into it, we want to see that the solvent has some of the same intermolecular interactions that the thing we're trying to dissolve is. So if we have the liquid, that's called the solvent. That's what we're going to dissolve the solute in. So we want the solute to have the similar intermolecular interactions that the solvent has, and vice versa. And then it's more likely to dissolve. Okay. So if we think about that in an ionic solid, we have to break up the ion-ion interaction by surrounding each of those ions with something that can have a dipole on it to support a whole bunch of them to support all of that charge. And then that solvent has to pull the other ion and surround it and pull it around and surround it. So that's what the dipole-ion interaction has. But most of the time we're looking at dipole-dipole or other interactions. So let's look at some other solubility trends. So in general, hydrocarbons dissolve hydrocarbons because they only have induced dipole interactions. Okay. So then that means that things that have polar bonds tend to dissolve in other things with polar bonds because they have a permanent dipole. And you get the dipole-dipole interaction. Just because you have a carbonyl in your solvent and a chlorine bond in your solute, those are polar bonds. We can still have them interact together to have a dipole-dipole interaction, okay? So polar materials will tend to dissolve. Now, there comes a point where we have what we call weak polar bonds. And that's where we have something like the carbon-nitrogen bond, which is not very polar if it doesn't have hydrogen bonding, or the carbon-oxygen-carbon bond, if it doesn't have that hydrogen bonding, we call that a weak. And so it might dissolve in a polar compound, but because it's not a strong dipole, it might dissolve in a non-polar compound as well, depending on the number of carbons we have. We have a couple more minutes, really. It's only 11. So let's look at this as a function of this compound here. And we want to look at how we can dissolve something. So let's start with this compound here. 5 carbons. What kind of interactions does it have? It's just induced dipole, right? And so we're going to try to dissolve it in 2 different things. We're going to try to dissolve it in carbon tetrachloride. And we're going to try to dissolve it in water, CCl4. Okay, CCl4 is non-polar, right? But it has polar bonds, but the net molecule itself is non-polar because they all cancel out. So if we have a non-polar compound and a non-polar solvent here, is it going to dissolve? Yes, so we're going to probably dissolve that. Now we have this right here, and we have something that hydrogen bonds and has dipole interactions. Is it going to dissolve? No. So it's not, because it doesn't have close enough interactions. Okay. But what if we take something that has a permanent dipole, CH3, CH3, and we try to do the same thing, CCl4 and H2O. Okay, permanent dipole. So is this compound acetone? Is it going to dissolve in water? Both have dipoles. They're going to be, yeah, definitely. Yes, soluble in water. We have a permanent dipole. We have a non-polar molecule with polar groups. Is it going to dissolve? Yes. So it doesn't have to be purely one type of interaction. It can be a combination as well. Okay, questions on that?
What would that interaction be?
So we would have a chlorine right here with its lone pairs around it. And this is the partially negative side. This is the partially positive side. We have the carbon with the partially positive side of the carbonyl. This partially positive carbon of the carbonyl is attracted to the partially negative chlorine of the carbon tetrachloride. It's only interacting with one side of the molecule. The molecule itself is nonpolar, but that side is. Does that make sense? So what we can also say is that by adding an OH to this group here, will it now dissolve in water? Yes, because now it has a polar group. And the rule of thumb is that if you have a polar group like water or a carbonyl compound, you can typically pull about 5 non-polar carbons into a solvent, a polar solvent. So if you got to this will probably dissolve in there. But if you got to heptanol, right here, 7 carbons, that won't dissolve in water. But you can get 5 carbons per functional group. So if we put another OH on here, heptane diol will dissolve in water because you have less than 5 groups, 5 carbons per functional group. Okay, so it's 5 carbons per functional group is the rule of thumb. It's pretty close to that. Okay, and I'm going to stop there. Yeah, I'm going to stop there. And if you want to continue on and look at the rest of these. No, I have 2 slides left. Anyway, this is the review of everything we just talked about today. And this is saying that you can have a molecule that has a hydrophilic side, a side that will hydrogen bond, and a hydrophobic side, a side that won't hydrogen bond. And you can still use it for both properties. It'll dissolve in a nonpolar solvent sometimes, and a polar solvent in other times.
Would it partially dissolve or would it dissolve whole?
Depends on if you turn this into a salt, you can get it fully dissolved. If you have it a polar solvent with a nonpolar side, you can get it fully dissolved. So it's all about that. But I will do those two slides on. Those two slides will actually, hydrophilic and hydrophobic will not be on the quiz on Monday, but all those interactions will be. So everything up to those interactions will be on the quiz on Monday. Right? Stay safe, watch your emails. You might not have to come to class tomorrow. Or you might not have to come to campus tomorrow. I don't know about your class.
In the first couple minutes of class.
The first 15 minutes of class.
So I'm getting it. I have 1.5 time right now, but I'm supposed
Okay.
to have double time.
Okay.
I was gonna ask I had Dr. Davidson,
Uh-huh.
Mary Patterson this semester, and then also Dr. Kavita, and so they recommended for me to go to the testing center. It doesn't always work for me because I just now picked up another full-time job.
Oh, no.
And full-time school, and they only have certain times, like it's like 2 times per day. If that is the case for this class, how would I work that out?
Okay. What we can do is let's try the testing center. It's always best because it's always the quieter environment. Number 2, what we can do is I actually have this class earlier in the day. We can meet before class to give you that 2 time.
So I have lab right before that.
Okay. We can move to an online quiz.
Okay.
Okay. I do have some people that prefer online quizzes because of different issues. And so we might do that. Do you want to try that instead?
Yeah, we could try that out.
Okay, email me and say for Monday's quiz, we'd like to try it online because of your accommodations, and then I'll get it all set up for you. Okay?
Thank you.
Stop sharing. Let me just stop recording.